Okay, so this is the outline of chapter 24 about the electric potential. So first we will introduce what is electric potential, and then we'll talk about equipotential surfaces and the electric field. Okay, so the equipotential surfaces is related to the electric field lines. Okay, so also a way of visualizing the E field or the electric potential, something like that. And and then we will talk about how to calculate the potential, the electric potential due to some structure like charged particle, the easiest case, and then electric dipole, and then also continuous distribution, just as what we did in chapter 22, but at that time is for E field. Here we do this for the potential, okay? And then we'll talk about the calculating the field from the potential, and then the electric potential energy of a system of charged particles. Okay, so electric potential energy, of course, related to the electric potential, and then the potential of a charged isolated conductor. Okay, so here is the definition of electric potential. So it says electric potential V at the point P in the electric field of a charged object is defined like this. Defined like this. V equals negative W infinity over Q0, or it is equal to U over Q0. Okay, so of course Q0 is still the positive test charge, and W infinity is the work that would be done by the electric force on a positive test charge Q0. Okay, so it's related to the work done, and this work done is the negative of the electric potential energy, just as what you did for the mechanics. Okay, mechanical system. Actually the same concept, but it is for the electric field. Okay, so here it's just like you try to put positive test charge from infinite far away to some point P you concern, and then so W is the work done. You try to move the charge, and in this case you will gain some electric potential, because if this bar, such as say this bar is the positive charge, and then you put a positive charge here, okay, you will store some energy in this system, because these two positive charges will repel each other. If this charge is at infinite far away, then R it tends to infinity, which means there are no Coulomb's force. So in such a way, there will be some sort of stable, but if you put a charge here, then there will be some energy stored in this system, and this is the U, the electric potential energy here. Okay, so for this one, it is just to move this Q to the other side, so you have the potential energy equals Q times the electric potential, or sometimes I just call it voltage, but although voltage is somehow a circuit theory term. So, and potential is actually a field, so sometimes they are the same, but sometimes they are not. But actually I'm a circuit guy, so I tend to call V to be voltage, so so you bear in mind that when I talk about voltage, maybe it's referred to the potential. Okay, so there are some simple equations. So it's just like change in electric potential. So in the space, suppose you have 2 points. So suppose you have an initial point and a final point, and then for the initial point, it has an electric potential of Vi, and then at the final point, it has a potential of Vf, and then suppose you move a positive charge from I to F, then the potential will change, and the change of this potential is Q times delta V, Q times delta V, Q times Vf minus Vi, nothing special. And yeah, this is similar, so W is just negative delta U, which is negative Q delta V, okay, so. And then here, the third point is the conservation of energy. So usually we can assume for this kind of system, yes, we don't have energy loss. Usually for some charge system. So in such a way, we can have a conservation of energy. So which means that the total mechanical energy is like it's like the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. Okay, so this is like the left hand side is the total mechanical energy at the beginning, and the right side is the total mechanical energy at the end. Okay, so this is, and they are equal. And yeah, actually we assume there is low energy loss, then there will be conservation of energy here. And if we slightly move around the term, let's say we try to move this term to the right side and move this term to the left side, we will have Ui minus Uf equals Kf minus Ki. Okay, so the right side will be delta K, which is the change of the kinetic energy. And then this one is actually negative delta U, which is the negative of the change of the potential energy. So this form is still the conservation of energy. Okay, although this one is more intuitive. Okay, 这个比较直观一些. But actually this one is still the conservation of energy. So it is nothing but delta K equals negative delta U. Negative delta U is negative Q delta V, which is this one. Okay, and also we have a work by apply force. If we apply force to a system, then yeah, there will be some work going in or going out from the system. So in that case, there will not be conservation of energy. So actually we need to add this term there. Yeah, I think you should be familiar with it for the mechanical system. So I don't try to elaborate more. Okay, so here we have a simple sample problem. So it says electrons are continually being knocked out at air molecules. 就是在这个大气里面的一个空气的分子啊，就是那个电子会被敲出来了啊。那 in the atmosphere by cosmic ray cosmic ray particles 就是一些宇宙的射线嘛。Okay, so coming in from space. 那这是一些所谓的 high energy particle 嘛，就第21章最后有说过一些所谓的一些high energy particle， 就是一些所谓的gamma ray 啊，或者是 X ray 之类的。Once released, each electron experience an electrostatic force due to the electric field that is produced in the atmosphere by charged particles already on Earth. Near Earth's surface, the electric field has the magnitude E equals 150 Newton per Coulomb and is directly downwards. Okay, so here we assume there is a E field which is uniform and then pointing downward with this magnitude. What is the change delta U in electric potential energy of a released electron when the electrostatic force causes it to move vertically upward through a distance d equals 520 meters? Through what potential change does the electron move? Okay, so this is pretty easy. So the work done will be nothing but F dotted with the displacement. Okay, F dotted with the displacement. Okay, so suppose this is an electron which is a negative charge and then E field is pointing downwards. So the Coulomb's force acting on this electron will be pointing upward. And we also assume that the electron also move vertically upward. So actually D also moving upward. So F and D points to the same direction. So F dot D will be a positive value. And actually it is like F equals Q times E dotted with E, and which is nothing but Q times E times D and then cosine of 0 degree, because E and D point E and D actually actually it is 180 degree. Okay, so here F and D points to the same direction, but E points the opposite direction. So here we have we have this one to be a -1, and so in such a way we have negative QED, negative QED, and then we can just substitute the numbers, so which is negative 1.6 times 10 to minus 19, and then times E is this one, and then D is this one. Okay, so it is 150 and then times 520. So this number is okay, so actually this one we have a negative sign here. So so in that case, so it becomes a positive, becomes a positive value. So it is actually 1.2 times 10 to negative 14 joule. Okay, so this is actually the work done. And actually it asks you the potential energy, the change of potential energy. And in such a way, delta U is actually negative W, which is negative 1.2 times 10 to minus 14 joule. And it also asks you what is the potential change. So the potential change is actually delta U over Q. So this is a negative 1.2 times 10 to minus 14. And this Q is an electron, so it is a negative 1.6 times 10 to minus 19, which is 4.5 times 10 to the 4th power volt. Okay, so actually this is or you can write it as a 45 kilovolt. Okay, 45000伏。 Okay, so this is just a very simple sample problem. So let's move forward. And so here we will introduce the equipotential surface 叫做等电位面 Okay, so here it says the adjacent points that have the same electric potential form an equipotential surface, which can be either an imaginary or a real physical surface. 就是可以只是一个想象中的一个面，也可以是实际的一个实体，就是实体的一个面啊，就是可以是空间里面的。Okay, so here it says, the work done. So it says the figure shows a family of equipotential surfaces associated with the electric field due to some distribution of charges. The work done by the electric field on a charged particle as the particle moves from one end to the other path. To the other of path 1 and 2 is 0. Okay, so let's see what it means. Okay, so here we have 4 equipotential surfaces, V1, V2, V3, and V4. Okay, and actually I think these are the electric field line. Okay, electric field line. Okay, so actually the electric field line must be perpendicular to the equipotential surface, or you may say the equipotential surface is a curvature, not a plane. Okay, so actually, strictly speaking, you can say, it is actually perpendicular to the tangent plane at that point. OK， 就是跟那个切面垂直，或者是你直接说跟那个曲面垂直或者正交也可以。OK, so here we can see the path 1. The path 1 is from here to here. Okay, from this point to that point. Okay, so path 1. So if you move a charge from this point to that point, okay, so so it doesn't go off from this equipotential surface V1, so which means that the potential change is actually 0, and in such a way there should be no potential change. Also, there's no work done. There's no work done when you move a charge from this point to that point. And then let's see for the second one. For the second one is starting from here on V3, going off V3 and then going back to V3. Okay, in such a way there is still no work done for this movement, because when you talk about the potential change, it only relates to the initial point and the final point. It doesn't relate it to the path, how you move from here to there, or you move along the same potential surface, or you move from here to there and then going back. Okay, it just relates to the starting point and the end point. And both of the points are on V3, which is on the same equipotential surface. In such a way, there's no electric potential change, so there's no work done. Okay, and the work done as the charged particle move from one end to the other of path 3 and 4 is not 0. Okay, path 3 and 4 is not 0. Okay, so here actually it's like you move from V1 to V2, or from V1 to V2. So which means that delta U3 is actually V2 minus V1. Okay, and you can also write it as W3 is V1 minus V2, which is negative delta U3. Okay, which is negative W3. Okay, and then for path 4, the starting point is still at V1 and then it go off a bit and then going back to V2. Okay, so actually delta U4 should also be V2 minus V1, okay, which is equal to negative W4. Okay, so actually it says it's not zero, but has the same value for both of these paths because the initial and final potential are identical for the two paths. Even though these 2 points are not the same, these 2 points are the same, but these 2 points are on the same equipotential surface. These 2 points are on the same equipotential surface, and then so the difference, the difference, which means the potential difference, will be the same. Okay, so this is a simple idea of the equipotential surface. Okay, so here we have some some mathematics. Okay, some rigorous definition. Okay, so here it says electric potential difference between 2 points I and F is Vf minus Vi, which is normal, and then equals to this stuff. So this stuff is negative. Okay, so you see an integral sign, and you can see here is E dot ds. It is not E dot dA anymore. In chapter 23, we have E dot dA, and in such a way it was a flux, maybe a total flux or a net flux, depending on whether the cold surface. Here it is not. So in that case, E dot dA for that one, integration of E dot dA, that was a surface integral, surface integral， 那个叫做面积分。And for this one, ds is actually a line integral， 叫做线积分，就少了一维的线积分。Okay, so yeah, and then here we have a negative integration E dot ds from I to F. Okay, so what does it mean? So let's see in this figure. Of course, we have a electric field. We have an electric field not quite uniform, so it can be applied for arbitrary E field. Okay, so in such a way, we define a path from I to F, which is a continuous path. 就是一个连续的路径，连着 I 跟 F， 连着起点跟终点了。Okay, so actually this one means that we try to cut this path into many small segments. Okay, try to cut it for many parts. Okay, many short parts, so that we can regard every short part is a straight line. Okay, and as much as we move the charge from I to F, so it has a direction. Okay, so the direction is somehow like this. Okay, so for every segment we can have ds. So maybe I just erase this stuff. Let's say for this one, we can have ds somehow pointing to the right side. Okay, ds. Okay, so this is a line vector. Okay, the magnitude is the length of the line, and then the direction is actually parallel to the tangent line of that point. 就是跟那个切线那一点的切线平行，而且那个跟它平行的话有两个方向，可以这边，可以那边了。那个方向取那边就是顺着这个 I 到 F 的这个方向。 OK， 就是也是跟那个 E 到 DA 类似嘛。E 到 DA 的话，就是 DA 的话一定跟那个切面垂直嘛，那也有两个方向。那如果是封闭曲面的话，就一定要向外啊。那这个的话就顺着这个路径。那所以 so in such a way for every segment you can actually calculate E dot ds. For example, for this point, you can see at this point E should be something like this. Okay. Yeah, because the E field line is somehow like this, so the E field at this point should be somehow like this. And then for this segment, you can calculate E dot ds, and then you try to add all this E dot ds together, and then we can write this sum, this Riemann sum, as this line integral. And as much as this is a inner product, so the answer will be a scalar. Okay, so we can actually add all this scalar together to be the electric potential difference, or sometimes we just call it V or delta V. Okay, sometimes we write it as delta V, sometimes we just write it as V, or yeah, something like just a notation. So sometimes we call it a delta V, but yeah, they sometimes just means the same thing. Okay, so in such a way, for the definition of the electric potential, it is actually this line integral. So you take the line integral E dot ds from the initial point to the final point, and then don't forget the negative sign. Don't forget the negative sign. And then simply speaking, we can choose Vi equals to 0, or just consider the difference to be the V, and then in such a way we have V equals negative this same line integral. Okay, and yeah, so this is a special case in a uniform field, 就是一个均匀的电场。The change in potential from a higher equipotential surface to a lower one, separated by a distance delta x, is delta V equals negative E times delta x. Okay, so this line integral, if E is uniform and E is has the same direction, or you can just count the x-axis component and y-axis component, and then it's shrink down to a multiplication. 就是如果是 E 是均匀的话，就是而且 E 如果比如说跟你考虑的方向是平行的，或者是你只考虑 E 在那个方向的投影的话，就是它就变成一个简单的乘法，就是 delta V 等于 negative E 乘以 delta x. Okay. And of course, when we introduce a new variable, we need to mention the SI unit. For the SI unit, potential delta V, the SI unit is nothing but SI unit for V is V. Okay, V. Okay, actually, the long form is volt. Okay. And even for ECE student, I saw many students can't distinguish what is volt, what is voltage. Okay, volt is the SI unit. Volt is the SI unit. Okay, of course it is named after a physician. Okay, 福特嘛. And actually voltage is some short like the potential. 就是 voltage 是电压，这个是电压，或者是电平，或者是反正有很多叫法。Okay, volt and voltage are different. Okay, volt is a unit, and then I usually heard them say 3.4 voltage. that's not correct. Yeah, so keep in mind that. Okay, so volt. Okay, so in such a way, it mentioned that another SI unit for E, okay, is V over M. Is V over M. In chapter 22, when we learn about the definition of E, we know that the SI unit for E is N over C, Newton per Coulomb, because it comes from E equals F over Q, F over Q. So this is Newton, this is Coulomb. And here, this is V. This is also the E field, and then this is meter. Okay, delta X is a length, so the SI unit is meter. So in such a way, from this equation, we can know that another SI unit for the E field is V over M. So both SI units will consider to be correct. Okay, so we can use either one. Okay, so up till now, any questions? 有没有问题? Okay, so here we have another sample problem. So for part A, it asks 2 points I and F in a uniform E field. The points lie on a same E field line, not shown, and are separated by a distance D. Okay, so you can see here, this is I, this is F, and then with a distance D. Okay, so find the potential difference Vf minus Vi by moving a positive charge Q0 from I to F along the path shown, which is parallel to the field direction, which means that we move the charge like this. Move the charge like this. Okay, so yeah, so here Vf minus Vi, which is nothing but negative integration of E dot ds from I to F. Okay, so here we can see the E field. The E field. Yeah, the E field is pointing downward. Yeah, doesn't mention here. But anyway, the E field is pointing downward. Yeah, because actually it's parallel. It actually mentioned that the path is actually parallel to the field direction. So if you move this like this, and then the E field also pointing to the same direction. Okay, so in such a way, yeah, this is from I to F. In such a way, ds is also pointing downward. Okay, because it's straight line, so the tangent line is itself. So yeah, ds is pointing downward. Okay, so you can imagine like ds E dot ds will be a positive number, and then they are pointing to the same direction. So E dot ds becomes E times ds, and then times cosine of 0 degree, which is 1. So I don't write it out. Okay, so here, as much as E is a uniform in the space, which means that we are integrating a constant, or you can just put it out E times this line integral, and this line integral, which is nothing but the length of this line, of this path, which is d. So this is nothing but negative ed. Negative ed. Okay, so this is easy. And then now find the potential difference Vf minus Vi by moving the positive test charge Q0 from I to F along the path ICF. So this is ICF. Okay, still the E field pointing downward, but yeah, we try to move to the right side first, and then we move back to this final point. Of course, just as what we mentioned, the potential difference doesn't relate it to the path, but actually this sample problem try to verify it once for you so that you have some idea. Okay, so yeah, after the calculation, although the steps are different, but finally the solution will, the two numbers will be the same. Okay, so here we try to calculate Vc minus Vi first, and then we try to calculate Vf minus Vc, and then we add them together so that we finally still have Vf minus Vi. So for Vc minus Vi, which is negative, integration of E dot ds, and then from I to C, okay, which is this path, Okay, so this path, ds is actually pointing to the right side, and E is pointing downward. So you can see that E dot ds is actually E times ds cosine of 90 degree. Cosine of 90 degree is 0. Okay, so this is nothing but 0. Okay, negative 0 is 0. Okay, so next we have a Vf minus Vc, which is negative integration of E dot ds from C to F. Okay, from C to F, which is from this point to here. Okay, so here we can see ds is somehow like this, and then E is actually like this. So they have a 45 degree angle in between. So it is actually negative integration of E times ds, and then cosine of 45 degree. Okay, and then from C to F, Okay, so this cosine of 45 degree is square root of 2 over 2. Okay, so and then E is still a constant. Okay, we can still put it outside, so it is nothing but negative square root of 2 over 2 times E, and then integration of a ds C to F. Okay, so this line integral is nothing but the length of the line. Okay, so let's see if we try to connect these 2 points I and F. So this will be so this right angle triangle. Okay, this is 45 degree, this is also 45 degree, which means that so this is D, this is also D, and this one will be square root of 2D according to the Pythagorean theorem. Okay, something like this. So this is a negative square root of 2 over 2E, and then this one will be square root of 2 times D. Okay, so finally this square root of 2 and 2 cancels. It finally turns out to be negative ED, and then finally we can write it as Vf minus Vi equals Vf minus Vc plus Vc minus Vi, which is negative Ed, plus 0, which is negative Ed. So it will be the same value as the previous one. Any questions? Okay, so here we talk about the potential due to a charged particle, okay, which is also like the easiest case, but this time it doesn't really look it doesn't really that simple. We need some integration here. Okay, so here the electric potential difference between 2 points I and F is this one, VF minus VI. Okay, and then equals negative integration of E dot ds from I to F. So this is nothing but the definition of the electric potential. Okay, here for the radial path, we try to take the final point is at infinitely far away, and the initial point is the point we concern. Actually, R is this point. And this is a small r. So we try to move a charge from point P to infinite far away. Okay, so this is the initial point, and the final point is at infinite far away. And then here we call this the R axis. We call it the small r axis. Okay, so for the starting point is R, small r equals to capital R, and then the final point will be R equals infinity. Okay, and then here we assume it is a positive charge. So it will be generate E field pointing upward on this axis, and also it has the same direction as the ds, and then the ds we will consider it as dr times ds or s hat, something like that. So it just means that we try to take the r axis, which is parallel to the ds. Okay, so finally we just write it as dr, and also this dot product just become a multiplication, because E and ds just parallel to each other. The angle between them is 0. So we have E dot ds is E times dr. So rather than writing it as ds, because here we use the axis of r, so we just write it as dr. Okay, so actually we need to do this integration, and suppose we have some knowledge of the E field. The E field will be 1 over 4 pi epsilon naught. This is K times Q times over R square. So this is the E field. We will try to put this thing into here. Also, for the initial point, this is what we would like to find. So we try to assume Vi to be the V. The V is the value we would like to find. And for the VF is at infinitely far away. So we assume the potential energy will be 0 at infinitely far away, just like for the gravitational system. So similar case. So we have VF equals 0. So suppose we have this one to be 0, this one to be V. Okay, so in such a way, this negative sign and negative sign cancel. So here we have a 0 minus V equals negative, and then we try to plug this one here. Okay, so for this integration, it is dr. So only r square need to remain inside. we can just put a q over 4 pi epsilon naught outside the integral. So here we have a negative q over 4 pi epsilon naught, and then integration dr over r squared. This r squared is here, and then from capital R to infinitely far away. Okay, so in such a way, this is actually r to the negative 2 dr integration. So the answer will be r to the negative 2 plus 1, and then over negative 2 plus 1, and then evaluate from r to infinity. Okay, so in such a way, this negative sign and this negative sign cancel. So here we have a positive argument here, but when we try to evaluate this 1 over r from capital R to infinity, so this one will become 1 over infinity minus 1 over capital R. So there will still be a negative sign. So this one will become negative q over 4 pi epsilon naught, and then times 1 over capital R. Okay, so you can see here it is a negative v equals negative kq over r. And finally, we try to switch back this capital R back to a small r, just for a notation. So finally, the expression becomes v equals k times q over r. Okay, or you can just write it as a k times q over r. So another similar expression like the Coulomb's force and the E field. So for the E field, it is a k times q over r squared. For the Coulomb's force, F equals k times q1 q2 over r squared. Okay, so sometimes 2 in the numerator, 2 in the denominator. 1 in the numerator, 2 in the denominator, and then 1 and 1 for both. And later on we also have the potential energy. Potential energy will be k times q1 q2 over r. Okay, so we have all the 4 combinations. But anyway, this is the potential due to a charged particle. Okay, let's have a